In our last segment, we're going to talk about waves and quanta. Um, when we talk about light, we're actually talking about an electromagnetic wave. This is the same thing as a radio wave or a microwave. Light is actually the same thing as those. It's the same kind of wave, and the general term is electromagnetic wave. One of the key features of electromagnetic waves is they all share the same velocity, which is the speed of light, which is the speed of light in free space and essentially in air, 2.99 times 10 to the 8th meters per second. Nothing goes faster than this, right? And in fact, this is the only scale we really have in the universe for a lot of things. So if you decide to go on to get a PhD in physics and specialize in particle physics, essentially we'll just set this to 1 and call everything else some scale relative to the speed of light. Um, and here's an important thing about light and electromagnetic waves and all waves in general. The velocity of the wave, right, the c, is equal to the frequency times the wavelength. Now we've been talking about the wavelength of light already is going from about 400 nanometers up to around 700 nanometers, actually the visible spectrum that we see with our eyes, right? The only thing special about the visible spectrum is that we see it with our eyes. And there's not much difference in UV or infrared between what we see and those. The UV is a little bit shorter wavelength, the infrared is a little bit longer wavelength, and because the speed is the same for all of them, once you know their wavelength, you can calculate their frequency, or once you know their frequency, you can calculate their wavelength. So let's look at the electromagnetic spectrum. All right, there's this itty bitty piece, and this really isn't even a scale because it's even narrower than this. There's this itty bitty piece we call the visible spectrum, and you'll notice this is a log scale around the bottom, right? This is frequency, and this is 100. This is 10,000. This is a million, right? This is these are all factors of 100 as we jump up the scale. It's a log scale here. On the top, you can see the scale of the wavelengths. So down here we have frequency, up here we have wavelengths. So as frequency goes up, wavelength goes down, right? And then we hit the visible spectrum where everything's on the order of a few hundred nanometers. A nanometer is 10 to the minus ninth meters. So visible spectrum, a few hundred nanometers. All right. As you can see here, infrared, and these boundaries, right, are somewhat arbitrary. I mean, there's nothing that really defines an electromagnetic wave as infrared other than we pick a range and say that's infrared, right? So there's overlap between infrared and microwaves and radio waves. There's overlap between ultraviolet and X-rays, and overlap between X-rays and gamma rays. Some of this X-rays is a matter of how we produce them, all right? The production methodology for X-rays is we accelerate electrons to really high speeds and we slam in them with stuff and we get X-rays. Gamma rays are produced through other methodologies. Um, Microwaves we can produce, well, you do produce all the time, right? You produce microwaves in your home on a fairly regular basis, probably. Radio waves. You're bathing in radio waves right now in all likelihood. Radio waves are all over the place. And then there are subsets of those for AM radio, FM radio, TV, all of that. So this spectrum goes on essentially forever out that way, except there's some, it's really hard to get some of the higher frequency or shorter wavelength stuff produced simply based on the scale of atoms and things like that. Okay, so what we see is a little bitty piece of it. When we're talking about remote sensing, we actually extend up into the ultraviolet sometimes with remote sensing. Definitely extend down into the infrared, and then microwaves. We use those all the time. We use microwaves all the time in remote sensing for radar, right? Big part of remote sensing is radar and sideband radar and all kinds of things like that. And if you look at the size of microwaves, right, on the order of a few centimeters, that tells you a good bit about what size item you could actually see with microwaves, right? We can see very tiny things with our eyes because the wavelengths we're using are very small. Microwaves, not so much. If we saw with microwaves, I could see the cup on my desk and I'd see my pins, but if I took the cap off my pin and set it on the desk, I might lose it. Might not be able to see it. Might not be able to see my thumb drive. Be hard pressed to see my business card sitting on the desk because it just doesn't stick up enough. All right, so we have this spectrum of wavelengths or the spectrum of frequencies, whichever you want to look at it, that make up the electromagnetic spectrum, right? Well, there's something we discovered about this, and this is some work that happened around the turn of the century, last century, 1800s, 1900s. And they noticed when we started looking at the spectrum, the actual light we get out of, say, oxygen. Well, you can see there are very bright lines at discrete places, right? These very bright lines. And we began to understand that there was a structure to the spectrum emitted by different atoms. And in fact, you can take different atoms, look at their spectrum, and figure out which atom they are based on their spectrum. What light do they actually emit and absorb, right? Well, this led to the notion of quantum mechanics and to the discovery that light itself is actually quantized. So while we may view light as a wave, right, the energy in this wave comes in distinct packets called photons, which you're familiar with that term, but the energy in an electromagnetic wave comes in a distinct packet that we call a photon. The photon energy in an electromagnetic wave is what we call Planck's constant times the frequency, or you can rewrite it as Planck's constant times the speed of light divided by the wavelength, right? And the Planck's constant is this number right here, 6.626 times 10 to the minus 34 joules per seconds. For a lot of work, we convert Planck's constants from joules seconds to electron volts seconds, just because the electron volt is a much more useful energy unit when talking about atoms, which is what photons are interacting with. So in electron volt seconds, 4.14 times 10 to the minus 15 electron volt seconds. And we could actually just take this Hc, make it a constant of 1240 electron volts times nanometers. And so you put in the wavelength in nanometers. All right, you take this number, put in the wavelength in nanometers, you get the energy out. Well, what does that tell us? This chart over here gives us some things. If we're looking at red light, right, the red light you see, the energy in a single photon from red light is about 2 electron volts, a little bit less than that. The energy in a single photon that we call blue light is about 3 electron volts, maybe just a little bit more. All right? So that's the energy scale for the light that we see, and you can see what does this do to atoms? Well, energy between outer electron shell and atoms. So this is enough energy to excite an atom, or it's enough energy to change, to break apart a weakly bound molecule. It's enough energy, when you excite an atom, it's enough energy to put an atom in a new state, which is essentially what happens when we are seeing with our eyes. We're exciting the chemicals in our cones to give us a signal. We can vibrate molecules, right? Vibrational energies. Way down here, 10 to the minus fifth electron volts, right? That's the order of the rotational energy of molecules. And this is actually very important. You actually use this all the time. This is the order of, this is on par with the energy in a microwave oven, the photons in a microwave oven. And the reason the photons in a microwave oven, the reason all of our microwaves for the most part run at the exact same frequency, is that they are tuned to hit a rotational resonance in water. All right, and so your microwave turns on and all these little photons start hitting the water molecules and causing them to spin very fast. An individual photon hitting a water molecule pumps its kinetic energy up to where the temperature of that molecule is a few thousand degrees, and then you have to let that temperature dissipate. This is why microwave ovens are really bad at cooking some things, and Other things, if you're going to cook them, and turn them on and turn them off and turn them on and turn them off, because the individual water molecules get very hot, and you need to let that energy dissipate. Um, and this is also down in the region where we are using radar. And so this is one of the reasons radar antennas are so big, for a couple of different reasons, right? Radar antennas are big because, the microwaves themselves are much larger. You can even easily get up to a meter or 3 meters on microwaves, from 3 meters to 3 centimeters down to, this is going to be a third of a millimeter down here. Um, so your apparatus needs to be on the same scale as the microwaves you're trying to use. That's part of it. The other thing is, unlike these photons, where an individual photon from red light is 2 electron volts. Well, an individual photon from a microwave is around 10 to the minus fifth electron volts. So you need to capture a lot more of them and use a lot more of them to actually get enough energy in the electromagnetic wave to be detecting it and seeing things. So here, down in these ranges, a lot more photons involved in terms of getting things done, where up in these ranges we get away with much fewer photons, just because there's so much more energy per photon. One of the reasons we know this happens is some work Einstein looked at, which is the photoelectric effect. Um, and we can see that photons have particular energies by looking at what happens to electrons in a material when you shine a light on them. It doesn't matter if you have a light that's below this binding energy frequency here. Um, it doesn't matter how bright it is. It doesn't knock any electrons out of the material, because there's just not enough energy in any one photon to do that. And the interactions are happening on a photon by photon basis. But as soon as you cross the threshold, all right, as soon as you cross this threshold, and now you're at the point where an individual photon has enough energy in it to break an electron free, you see electrons start to pop out of the material. So that's an important concept for understanding how we use photons, right? In a charge coupled device, a CCD camera, the photons hit an individual pixel. So it's individual photons hitting individual pixels and depositing energy there. And the energy in the photon hitting the pixel, because charged CCD pixel is arranged so that there are a lot of charges that are somewhat loosely bound, if not bound at all, to anything. And an individual photon has enough energy in it to move a large number of charges. And so that gives us a good amplification of the signal individual photon to a large number of electrons. Um, we have some structures, CCDs, I don't know it. In physics, we use some where, the multiplicative factor is tens of thousands, right? In a CCD, I imagine it's tens to hundreds. More electrons come out than photons went in. But that lets us be very sensitive to individual photons on a CCD. Now on the human eye, that's just not the case. You need several photons before you begin getting enough signal to see anything. For the CCD, we can catch individual photons hitting the CCD. And that is exactly how, in the optical range, you should think about everything. An individual photon is coming in, it's hitting some detector, and it is changing that detector in some way by depositing the energy in that detector. It's either knocking electrons free or it's changing chemical bonds, right? So those are the key elements that we're after with these photons, right? In the optical range, we're changing the state of matter, or we're knocking a bunch of electrons free, um, and we're using that energy, right? And we're somehow detecting that energy and converting that energy into an electrical signal. Last little note: the upper end of the spectrum. Oh, X-rays you're familiar with, and by now you don't want to get a lot of those in your if you can avoid it. Gamma rays, you're not as familiar with. In nature, gamma rays come from a few sources. One is cosmic rays, very high energy particles hitting our atmosphere. The other is from radioactive materials. One of the reasons you don't want gamma rays get up into the wavelength range where the energy in them is enough to do things like edit your DNA. And you don't really want to be hit by radiation that can edit your DNA if you can avoid it. Unfortunately, it doesn't turn us into the Hulk. It tends to do other things to us. Okay, that's it. The key takeaway that is that we have an electromagnetic wave. The electromagnetic wave is anywhere along the spectrum. What we call optical spectrum is just this little bitty piece of it because that's what our eyes see. It's really the same thing all the way across. Same type of energy, all of that. The energy in a given wave is quantized, and we can use Planck's constant and the frequency, or Planck's constant, the speed of light, and the wavelength to determine what that energy per photon in the wave is. The key thing in terms of how we talk about it, we typically talk about light and gamma radiation in terms of wavelength. But when we talk about microwaves, we usually speak in terms of frequency, right? We'll talk about microwaves more in terms of their frequency than their wavelength. Although you will hear talk of millimeter waves. The upper end of the microwave spectrum will be millimeter waves. And that's a useful tool sometimes because it tells you about how big of an object you can detect. One last note on that front: Oak Ridge Labs during the Great War. Um, no, not the Great War, the Second War. The First War was the Great War. Oak Ridge Labs during the Second World War, they had a project going on. They were constructing parts for nuclear weapons. This required a lot of very fine detail work. And there was one woman that was much better at it than everybody else. And in fact, everybody else had to use a magnifying glass to actually put these little bitty parts together because they couldn't see well enough without the magnifying glass. And this one woman did just fine. Just gangbusters, worked without a magnifying glass, much faster than everybody else. So they got into investigating why is she so much faster. And it turns out she was so much faster because she did not see down in the red end of the spectrum, right? And you've got to remember down here we're talking about 700 nanometers. Up here we're talking about 400 nanometers. So this is much shorter. This is about half the length. The wavelength is about half the length as over here. It means we see fine detail better with blue than red. And they went through all the labs and they took out the white lights and they put in blue lights in all the labs, and that enabled everyone to work without the magnifying glass and everyone to work as fast as this one woman had been working. So that's a good real world example of how wavelength plays a part in terms of detecting objects, because this woman could actually see finer detail than everybody else. All right, that's it. Have a great day.